We will solve this today's LeetCode problem. This is a LeetCode hard problem. The question is remove max number of edges to keep graph fully traversable. So we have question Alice and Bob have undirected graph of n nodes and three type of edges. So we have given three type of edges. The first type is that can be traversed by Alice only. The second type is can be traversed by Bob only, and the third type is can be traversed by both Alice and Bob. Right. So we have given an array age where ages I is a type I, UI, VI. So this type is this type 1, type 2 or type 3, and U and V is the nodes which is connected by this edge, right? Represent the bidirectional edge of type between nodes UI, find the maximum number of edges you can remove so that after removing the edges, the graph can still be fully traversed by both Alice and Bob. The graph is fully traversed by Alice and Bob if starting from any node, they can reach all other nodes. Return the maximum number of edges you can remove, or return -1 if Alice and Bob cannot be fully traverse the graph. So basically, the question is asking us to remove the edges, remove the maximum number of edges, such that the Alice and Bob can traverse, can reach each and every node from starting from any of the node. Right? Basically, the question is asking us that we need to remove the max number of edges, the maximum number of edges from graph, such that such that Alice and Bob Alice and Bob can reach any node from each and every node, from each and every can reach each and every node from any node, right? That's the question, that the conclusion of this question, which the question is asking, right? So if you see, we have three type of edges which is represented as red, green and blue, right? So the red type is one, which is for Allies. Green type of edge is for Bob, and the blue type of edge is for both Allies and Bob, that both can be traversed on that edge, right? Basically, so we have given three type of edges, right? Three type of edges, right? So one thing is clear, that if I want to remove edges from graph, so basically what simply you can think of that, I will remove this edge and check for Alice and Bob both. I will again remove this edge, then check for Alice and Bob. Again we will remove this edge, then we will check for Alice and Bob. So the first approach, the brute force approach, which came in all our minds, that we will check for each and every node. We will check for each and every edge, right? That after every edge, that after removing this edge, whether whether we can traverse to each node for Alice and Bob or not, right? For Alice and Bob or not, right? The brute force approach is this. But if I do so, so for each edge, and for Alice and Bob both, for each edge, if I traverse in whole nodes to check that whether we can reach to each and every node or not, that will take uh, very much time. Of course, that will take O of E for checking E or each of edge. For that, if M is the number of edges present here, so O of M into O of N, uh, which is very large, because n is 10 to the power 5 given here, right? On edges length can be 10 to the power 5, so this is definitely giving tally, right? So will this will definitely give tally, right? This approach will definitely give tally, right? So we need to find some approach which can be doing less of that, right? So basically, if so in the graph, finding that for finding the edges which can be connected to particular Alice and Bob, how we think, right? So if you see, we need to find for Alice also and for Bob also, right? So there are two-person basically. So and both the person ages is different. Both the person ages is different. So can we simply consider Alice and Bob separately? Can I solve? Can I solve? Can I solve for Alice and Bob separately? Right? If both of the ages are different for Alice and Bob, and we need to solve for both. So can I solve for Alice and Bob separately, right? If I do so, how we will do that, right? Basically, to reach for each and every node, all the nodes must be in one component, right? All the nodes must be in one component. This is the first thing which should come in your mind. At for reaching each and every node from any node, from reach for reaching for for uh, for reach from going from moving forward to each and every node from any node, all the nodes must be in one component. That then only it's possible that I can go from any node to any node, right? That first thing is that all the nodes must be in component. Second thing is I need to I need to make I need to the edges remove the edges for Bob and Alice both, so that we so that we can reach each node from any node, right? This is the second thing. The third thing is, you see that we have type 1, type 2, and type 3. This type 3 is for Alice and Bob both, right? So it means that if the type 3 is present, it means Bob and Alice can traverse from that type 3. So suppose if we have given type 1 and type 3, or type 2 and type 3, so which is the preferable to choose? Of course type 3, because if I choose type 3, it can compensate to with type 1 and type 2 both of edges. It means I don't need both of the edges separately, I need only one type of edge, right? So if type 3 is given with any of the edge, we will give the preference of type 3, right? So if type 3 is available with any of the edges, or if the type 3 edges separately only, if the type 3 is available with any of the edges, we will give preference to type 3 for sure, right? For sure, because it will work for type 1 and type 2 both, because type 3 can be traversed by both alike. So third thing is this, right? So these three, if you use these three, you just need to think that how will I make all the nodes in one component. So basically, see, for components, what are the methods we have? For the components, if you see here, one thing to note that I need to remove the edges. So instead of checking for each and every edge, what can we do? Can we simply can we So if I don't remove edge, if I don't focus on removing edges, instead of that instead of that instead of focusing instead of focusing on removing edges, if I focus on creating an extra graph, creating a graph separately for Alice and Bob Alice and Bob by by creating by creating minimum edges for joining these and given nodes, right? And given nodes. So will this give me some ideas if I focus on creating a graph for Alice and Bob separately, instead of focusing on removing edges, which is already given the graph? If I focus on just creating a graph, will this work for me? So for that, what I will do, I will just see these nodes without edges, right? So if you see in the first example, this is 1 2, this is 3, and this is 4, right? So if I see separately these nodes, if I see separately, so suppose I'm creating for the Alice, right? I'm creating for Alice, and we have given edges, right? We have given edges, which I have given edges this, right? So if I focus on this edge, right, if I focus on this edge, how we will form this edge, how we will connect with minimum edges using these given edges, right? So I am doing for allies first, for first now I am doing for allies only, right? So see, this is type 3 and this is 1 2, right? So type 3 is will work for allies and bob both, right? This type C, let's make one part again. This is something like, and let's start from here. Okay, this will create problem. Let's make this here, right? And let's put it at here. Let's see, something is wrong. Okay, uh, okay, let's make it other types, right? So this is 1 2 3 4 for allies and this is for bob. Let's make it as this. So this is as bob and this is for allies, right? Now this 3 will work for 1 and 2 both, so I will make an edge for 1 and 2 both, right? I can make an edge for 1 and 2 both, right? So I will make an edge for 1 and 2, between 1 and 2 for allies and bob both, right? So it means I need this edge, I definitely need this edge, right? Okay, I need this edge, so I will count age for allies and bob both, right? I will count the age for allies and bob both because we need an age for both of them, right? Okay, see, 3 to 3, 2 3 have edges. No, this is not an edges, it is also already not connected. So 2 3 is of type 3, so we will give preference to this, right? Okay, so we give preference to 2 and 3, so we will connect this. I will connect this. Okay, so I will connect this. So I have connected. Now this 2 and 3 have connected, so allies and bob both need again one edge, so I will add them. Again I will see 1 1 3, so 1 is a type 1, so this is for allies only, and 1 3 is connected. So if we will see that whether we can reach from 1 to 3 or not, whether we need this edge to be made. So if you see in allies 1 2 and 3, we can go from 1 then 2 then 3, and 1 reachable from 1 to 3. So where do we need this 1 3 edge? No, we don't need this edge. It means this edge can be removed, this edge can be removed. Fine, this edge can be removed. So if this edge can be removed, this means this can be our part of answer, this can be our part of answer. So that, what does it mean? It means one edge can be removed, right? One edge can be removed, right? Again for 1 to 4, 1 is a type of allies type, right? And 2 4, so if you see this 2 4, if you see this 2 4, this and 2 and 4, it does not, is not connected, still is, it is not connected, right? It means this 1 and 2 4 can be connected, can be connected, right? So this 2 4 can be connected, so I will connect this because it is still not a one component. So for that I need to add, analyze one is one part, right? Again I will go to 1 1 2, so 1 and 2 is already connected with in the same component. So do we need this? No, we don't need this, so we will remove this. So I will add in remove part 2 3 4. Now the other thing is, this 3 and 4, is it connected in bob, because 2 is for bob. So is it connected in 2 and 4? 3 and 4, no, it is not connected. So do we need to connect it? Yes, we need to connect it. So there is again one need, extra one, uh, one edge needs to be added, right? Extra one edge need to be added, right? So finally if you see here, this 3 4, this 3 4, this 3 4 needs to be added, right? This 3 4 needs to be added, this 3 4 needs to be added. So one thing if you see here, if you one thing you see here, that how many nodes we removed. Okay, the first thing you need to check that all the nodes are in component for separately for allies or bob. So if you see, we can reach each and every node from any of the node. 1 2 3 4 all are in one component. For bob also 1 2 3 4 all are in one component. If you also see here, 1 3 4 all are in one component, right? We can reach from each and every node for both and allies. So one thing is clear, that how many edges can be removed? These two edges can be removed, right? These two edges can be we can remove here, and you can see the answer is also 2. So basically what I'm doing, basically what I'm trying to tell, so what I'm trying to tell, that we will try to create we will try to create a graph separately for for Alice and Bob using the ages given, given ages, using the given ages. But we will we will we will use we will try to use minimum ages required required to connect all the nodes for both Alice and Bob right. That's we want to do that's we want to do but this is just a this is just a showing you that, but how we will implement this, what we will use and something. So basically, if you understand that, if you know a concept called so basically you need to form a component. For components, one famous concept is DSU, disjoint set unit disjoint set union, right? Disjoint set union. So what does it do basically? Whenever we want to join we want to check or join or make a component for many of the nodes, what we do in DSUs, we use DSUs for basically to make to join separate unions to join separate unions in one component, right? Basically we want in one component, right? So what does this help? So what we are doing, we are sep- we are determining that all the nodes initially all the nodes are not joined, right? We are determining initially that all the nodes are not joined, right? And now I am trying to join all the nodes one by one. So to join this one and two I need to join I need to use this. See, these are the four separate components. If you see like this, that these four nodes are separate components initially, and when we want to join these components, this one and this two should be union, right? This one and this two union. And we want to when we want to connect this four, so this four is different component, that's this one and two. So when we want to join this four must be union with this one and two, right? After when this one and two is connected, after making this union, when this four is need to be connected with this one two, this four needs to be make a union with one two, right? So basically we use DSU here, and this DSU has a some standard template, right? This has a some standard template which needs to be followed, which I will show you, of course. So we will use a standard DSU here to to solve this problem, basically to solve this problem. And how will they use this? So basically DSU has some standard problem, the standard template, and we will use this that standard problem only to solve this problem. So if you don't know DSU, I will understand you make understand your DSU in this video also. But if you don't understand DSU still, so I will prefer to I will tell you to first learn DSU by reading any article or from any of the GFG or Code Forces or CPP and friends. Then you come to this. Otherwise I will make you understand in this video, but you will need to better understand the DSU concept, right? Then you can only solve this problem, basically, right? So basically what DSU do, it joins the different nodes in one component, right? So we will use that. So how we will use that? So see, one thing is here that this 1 2 3 4 is a separate component, right? And we are doing that, we are moving in this edge, we are moving this in edge, and we are giving preference to 3. So basically after using DSU, we need only these three things. We need only this thing, that we will give preference to type 3. We will make two components for different for Alice and Bob, and check that how many edges can be not taken from these edges. The edges which are given here, these are the edges to make this graph, right? These are the edges which we make this for this graph. So which edge cannot be taken for which edges cannot, which is not needed, we will count that only, and we will return that uh, at last, after checking that whether for Alice and Bob can we create a component for Alice and Bob separately, so that I can reach each and every node, right? Basically I will do that. So you see here that Alice and Bob can make a component, a single component where all nodes are connected with each other, right? So we will use a standard DSU. So for that, we everyone uses the same template, right? Basically everyone uses the same template. I will also use the same template. I will not give I will not give you some any other kind of code or something. That's the TSU template which everyone uses, and I will also use that one. So basically I have already written this TSU template. So you will find this template in any of the place, right? So this is the standard template. I will just copy paste here, right? See, this is the DSU template. This is the DSU template which everyone uses. So basically what this DSU do, it will create a parent array and the rank array. And this DSU, this is a just a representation of how we use classes. How we use classes in C++ is basically an oops concept. So basically this public, what this public do, this public will give us that we can use these functions whichever written under this public. We can use this in different classes or function by making an objects, right? Making of DSU objects, right? So this DSU will initialize the rank, the parent for that particular object. This find parent will generate a parent, that whether I have a parent that see, yesterday we have solved an ancestor problem, right? Remember, yesterday's we have solved an ancestor problem. So this find parent will the same as an ancestor problem, that this find parent will show you that whether the current node has same ancestors or not, right? And this union by rank is for path find and path compression. This is for path compression, right? This is for path compression, right? So basically we will use this template for DSU to solve this problem, right? So how we will do that? Let's just try to use this DSU concept. So first thing is that what we will do, when I'm using this, when I was solving this problem, this 3 1 and 2, first things for Alice and second is for Bob. So what we do, we will use the two components for Alice and Bob separately. We will use two DSUs. So basically, we will use these two DSUs for Alice for different Alice and different Bob, right? And what we do, we will check for each and every node. So the first stage is 1 and 2, between 1 and 2. Right? The first is 1 and 2. So this is 1, this is 2, this is 3, and this is 4, right? And the same goes for Bob also, right? Okay, same goes for Bob also. So 1 and 2 of type 3, it means it can go move in both of the Bob and the Alice, and we are creating it separately for 1 and 2. So what we will do, we will check for 1 and 2. We will check for 1 and 2 that whether we have whether we have whether we have 1 and 2 in same component or not, whether we have in same component or not, right? So for that, what we will do, we will check for this union. We will check for this union. We will check for this union by rank, that whether we have this 1 and 2 edges, this two edges in one component or not. So for that, I will check for its parent. I will check for its parent. Why we will check for this parent? So basically, to check for this parent, suppose this if you see in the example 4, if you only consider one edge on this at a time. So suppose I want to check for 4, right? From where we have started this 4. Remember the last ancestor problem, right? This 4 ancestor is 1, right? 4 ancestor is 1, means this 4 has started from 1. Okay, and also this 3 has started from 1, right? So it means this 4 parent is started from 1 and this 3 is started from 1. So I'm sure about that if 4 and 3 has the same parents, ancestor parent in any of the places, that this 3 and 4 will be in the same component. That's why this it has the same parent. I'm sure about that, right? So that's what it is checking, that union by rank, that it's I will find parent. So if U has a parent and V parent, both of the nodes parent is same, it means I have a same component. So if it has the same component, I don't need to make create an extra edge for that. So I will return a zero for that, right? I will use this union bank. I'm just making understanding you this code with the help of example to make you understand some DSO concepts here, right? Otherwise, if both of the parents is not same, what we are doing, we are we are creating an edge using this. We are creating an edge using this. So what we are doing, we are using a rank. We are using a rank, union by rank. There are two concepts: rank union by rank and union by size. There are two concepts. You can use this by union by rank or union by size. I have uses by union by rank, right? So I don't know how much you are understanding this, but I literally request you to see DSU, learn DSU concepts, then solve this problem, because this is very hard. This is hard problem, you know that, and you need to. And DSU is very advanced algorithm, so you need to learn DSU first, and then you will understand better this, right? I cannot understand make you understand this DSU here, because that will itself demands an extra video. I will make that, but for solving this problem, current problem, I will make you understand this, right? So just understand that this will create an extra edge between this u and v if both of the parents are not same, right? That's what we need. And at last I will return one, because that will create an extra edge and we need an extra count of one. So that's why I return one, right? So basically, if this one and two, if this one and two are in the same component or not, if we check. And if both are not checked, so that will create an edge. Same for 2 3 also. For Bob, this is type 3, right? This is type 3. So either, so this is type 3, so we need to check for 1 2 in both Alice and Bob, because type 3 can be traversed by both Alice and Bob. So I will check for 1 and 2 in both Alice and Bob. And then if Bob is and in any of the components, in any of the Bob or Alice, if both is not connected, so I will count by 1 for both of them, right? I will count for them. So this 1 and 2 will also be connected. Same for 2 3, same for 1 3, and same for 2 4, right? Again, for 2 and 3, what I will check, I will check for whether it is connected or not. So 2 and 3 is not connected and type is 3, so I will just connect this, and also I will connect this for also, right? I will also connect this also, right? Again for 1 3, again for 1 3, the type is 1, the type is 1. So we don't need to check for Bob. I will check only for Alice. So for type 3, 1 and 3 is connected. I will check for that. So if we see the parents of 1 and 3, if we check, so what I will check, union by rank, union by rank. And this is 1 and this is 3. So 1 and 3 parent, ultimately 1 and 3 parent is, what is 1 and 3 parent? So 3 parent is ultimately moved to 1, and 1 parent is already 1, because it is not started from anywhere. So the 3 and 1 parent is common, is common. It means we don't need to, don't need to add an extra edge for both of these. So that's why when both of the parents is same, it will return 0, right? It means I don't need an extra. So if I don't need an extra, so this 1 and 3 needs to be removed. So I will add in my answer that it's need to be removed, right? That's the concept. That's what we have seen here in this. That's what we have seen here. I'm just showing you that how we will use DSU to solve this. The same thing, how we will use DSU for that, right? The second thing is 1 to 4, right? This is again for allies. So 2 and 4, if we check for 2 and 4, it is, its parent is not same. Its parent is not same, because this parents is 1 and 4 parents is 4 again. So its parent are not same. It means I need to add this 2, I need this 4 with this component, right? I will need to add this 4 with this component. So what I will do, I will need to add this component. So I will add this, I will add an edge between 2 and 4, between 2 and 4, right? Right. So if you see, till now we have this 3 1 2 3 2 3 and 1 to 4, right? Right. So allies count is still, allies count is 3 till now, and Bob count is, Bob count is, Bob count is 2 till now, right? Again for 1 1 2. So if you see this 1 2, right? If you see in 1 2, 1 2 is parent is 1 again, because 1 2 is already connected, so we don't need to use this edge. It means we can remove this edge. We can remove this edge again for 3 4. This 3 4 is for type 2. It means Bob doesn't matter to Alice. So 3 4, we need to check for 3 4 that whether it is connected or not. So for Bob, I will check for 3 4 whether this 3 4 is connected. So this 3 parent is 1 and 4 parent is 4 itself. So I need to connect. So for that I need to add an edge and connect it. Right. At last, what I will check before returning this removed part, I need to confirm that whether we have all the nodes in my edge in my component, single component or not. Right. I need to check for that we have do we have all the nodes in my one component or not for both of Bob and Alice. So how we will check that? How we will check that all the nodes all the nodes are in the same components for Alice and Bob separately or not, right? How we will check that, right? So basically, if you see that if there are n nodes, we only needs n minus 1 edges to connect all the nodes in one component. See, this 1 and 2, 1 edge, 2 and 3 second edge, 2 and 4 third edge. So there are 4 nodes. So for connecting each and every node minimum times to be in the same component, we need n minus 1 edges only, right? So it means what I will check, and we are that's why we are counting this Alice count and Bob count, that how many edges we have. So what we will check before returning the this removed edges, before returning this removed edges, what we will check? We will check whether whether we have Alice count and Bob count equals to n minus 1 or not. If it is, then we will return simply our answer, which is removed edges. Otherwise I'm sure about that, we are not able to traverse either for Alice or for Bob with edges. So I will just return minus 1, which is given in the question, that if Alice and Bob cannot be fully traverse the graph, return minus 1. So I will return minus 1. That's what we use here, right? So basically, we are using DSUs for this. So whenever you find things like components and all, that something needs to be union by components, and we need to find components or check for components. So whenever you see for components type of questions to be solved you can think of DSUs. You can think of DSUs, although it's a very advanced algorithm. So basically you don't need to use this DSU algorithms for easy problems. So you can use this for means hard level of problems, or some high medium problems. So you don't need to use this for low medium problem for components. You can use this for high level problems for this, right? So whenever you want to use DSUs, for component type of question, whether you see to check components or to join some things or calculate it, so you can think of DSUs, right? That was the motto of this question, for forming this DSU. But how we will use this, right? How we will use this? So basically, what we will do, we will made a components for separately two components, Alice and Bob. So we will make two objects for that. One object is for Alice, which which what will have. So g for the making components, I need to pass number of nodes. So that would be n, right? And also I need to make a separate component for Bob. So I will make that, right? Now what I need to do, I need to give a preference to type 3 first, right? So what I will do, I will make all the edges which we want to form according to type 3 edges. So for that, what I will do, I will sort it according to the edges of type 3. First type 3, right? Then something else, right? So what I will do, I will just sort it of edge according to the types. So type is given at first position in vector. So I will just use this r begin, ages r end. So what I've done, uh, I have just sorted this age according to the type in decreasing order. Why? Because type 3 is this three number is greater than 1 and 2. So when I sort it according to the decreasing order, the three edges will come first. That's why I have done this, right? So I if I now I will what I will do, I will just make ages. I will just make ages to number of nodes and count that, right? Count that. So for that I will need to form a count alias, right? Second, count Bob. Also, an answer which will be for removing edges, which will calculate the removed edges, right? So answer is for removed edges, right? Removed edges. Count removed edges. Count removed edges, right? Now, if you see here in this, the first is the first part. If you see here, this edges I, this edges I, this is the representing edges I. So for E, first type is first type is type, right? And we know that we have sorted in decreasing order, so first type will be definitely type 3. So if type is 3, if type is 3, what I will do, I will I will check whether that we have both of the nodes. What are the nodes? This E0, E1 and E2, which is U and V. Okay, or let's don't make variables. Let's just take that alias, this alias dot union by rank, this union by rank, right? Whether we have the same nodes or not. So if I check this, so what is it will give? This is not exist, right? This is not exist. So if this give me one, sorry, if this give me zero, it means this will have if it has, if it is zero, it means this one and two is the part of same component of this for alias, right? So if, and what if it is given us one? So if it is given us one, it means both we need an extra edge for alias graph to connect this E1 and E2 combinedly, right? So what we will do, if we want this to be combined separate itself, so what we will do, we will combine this, right? We will combine this both of the edges, right? We will combine this. So for that, if the type 3, if this is a type 3, if this is a type 3 and this alias union by rank is combining with this, so I need to just combined for both of the allies and bob, right? Both of the allies and bob, the same thing will be done for allies objects also. Same thing needs to be allies for also, right? Because this type 3 can be traversed by both bob and allies. So if for any of them, if this allies, if it is not exist and we need an age for allies also, so we also need an age for bob also. I'm sure about that. If any of the nodes is not done by ages, so I need also for allies also, right? So what we will do, we will just check for bob also, that whether we need or not, right? Either allies or bob. If both, any of the nodes, any of the graph 1 and 2 nodes is not connected, so I will add for both of them. I will add for both of them in my answer. I will connect both of them. And also this age is done by, this age need to be counted for allies also and for bob also. So what I've done, I am checking that whether this two nodes is a part of component for allies graph also or bob also. If it does not, I will add age and count age, right? Otherwise, if both of the, if for both of the components this 1 and 2 is a part of the same component, so it means I don't need to use this age, right? So I can remove this age. If I can remove this age, I will just count this. I will just count this, that I don't need this age right now, right? Otherwise, if this is not a type 3, if this is only type 2, if this is only a type 2, what does it mean? Type 2 is for whom? Type 2 is for Bob, right? Type 2 is for Bob. So it means I just need to check for Bob. It doesn't matter for Alice. So what I will check, the same thing, bool not exist for whom? For Bob. So Bob union by array, sorry, for Bob union by rank, this and this, right? So I will check for Bob. If if it gives us 1, it means, if it gives us 1, it means we need an extra edge to connect both of the nodes. We need an extra edge for connect both of the nodes. So what we will do, we will just connect it and Bob count our Bob edges, right? Otherwise what we have left, type 1. So we don't need to specify check for that, because ultimately only type 1 is left. So we will and this is for Alice, this is Alice. So we will check for Alice, just need the same thing. We need to traverse, just change this to Alice and change this to Alice, and that's it. Okay, one thing also need to check, that if this 1 and 2 for Bob is already existing in the same component, so that does it means that this edge will not needed now. So for that I need to remove that. For that I need to calculate its answer. Just we had done this here, and also I will just use this here, same thing. If both of the nodes for Alice and for Bob already exist in their components, it means I don't need the current edge, right? So I need to calculate that edge and remove that edge. So I will calculate the count of that. Now this, what this do, this will give me the number of removed edges which we don't need, and also the number of edges we need for Bob and Alice, right? At last, before returning this answer, what we will check, that whether we have all the nodes in our Alice component and Bob component or not. So for that, what I will check, I will check that Alice, count Alice, right? Count Alice has n minus 1 edges, and count Bob also has n minus 1 edges or not. If it has, it means I have it. What does it mean? It means that all the nodes are in one component for Alice and Bob, both, for both Alice and Bob, right? For both Alice and Bob, right? That was it means. uh, just make an enter and use this as a command, right? That's what it means separately, right? So what we will do, we will just return answer here. Otherwise what we will return, -1, because if it is not n minus 1 for both, it means we don't have all the nodes in one component for Alice or either for Bob. It doesn't matter that which have not come one component, we will return -1 if it any of them has all the nodes in not in one component, right? So basically the DSU use is here, that to check to make all the nodes in one components for, right? So that's the whole concept of DSUs. So let's just run this. uh, Something is occurring, 59, some compilation errors. Let's see. Okay, bracket should be here again. Don't need. Okay, let's see again. So I think I have not made. Okay, yeah, sample case passed. Let's submit it. I hope I have not made any error. Yeah, we have passed. So after all, I have also got this. I have also got this for this component. So I will take a screenshot for that, right? So, and we have completed our June streaks. So basically now we will see this time complexity and the space complexity for this problem. So basically what we are doing here, we are using DSU, right? We are using DSUs. So so if you see DSU concept, right? So if you see DSU concept, So basically DSU takes the for joining all the components and all, it takes basically O of E, right? But we have also sorted according to the number of edges, right? Basically we have sorted according to number of edges, so that will take definitely for uh, O of E of log E, right? E of log E. So see, we have sorted according to the number of edges, so that will take O of E of log E. So E is number of edges which is present. So E of log E for definitely for sure, right? And for maintaining the DSU, for maintaining this DSU, this is O of log of n. This find parents is log of n, and this union rank is O of log of log of n in the worst case, but average time is O of alpha n. So what is alpha n? Or alpha is in n is Ackermann function. This is an Ackermann function uh, which is used for path compression by union by rank or size. You can use it, right? So basically, the time complexity for this union by rank is O of log of n in the worst case, but average. Let's write it here that for union by rank, the time complexity is average time complexity is O of alpha, which is how can I write? This is alpha, right? This is alpha, which is inverse Ackermann function. Inverse Ackermann function, which is inverse Ackermann function. Right? This is inverse Ackermann function, right? Basically, in worst case, it can go to O of log n, but in average time, it is O of alpha n, right? It is O of alpha n, right? So which is approximately takes O of 5, which is whose value is approximately O of 5 in the if you see its range, it basically O of 5. I will attach one article to see you this. You can see all this and read an article, you can better understand. But just to know you that this will take not more than O of log of n, basically, right? And for maintaining this union set, for maintaining this parents and all set, this it will takes O of n, because this parent resize n plus 1 and this is n plus 1. Okay, and also for n plus 1, why I'm taking this n plus 1? Because this uh, is started from 1, not 0, right? That's why I have taken O of n plus 1. Otherwise, if it is started from 0, we don't need to take n plus 1, we just need to take O of till O of n, right? That's the need of this rank and parent here, right? So basically this can be O of E log E plus O of n for the time complexity. And the space complexity would be so we have used the DSU concepts here, right? We have used the DSU concepts here. So the DSU concepts will take them because we have taken rank and the parents, and so and also we are using this Alice and Bob for storing that. So that would take definitely for O of n for rank, for parent also O of n. So that will definitely take O of n for storing this space complexity, right? So that's the whole time and the space complexity for this problem. And okay, now the thing is, can we optimize this O of E log E? Can we optimize this O of E log E? So the thing is here that what we are finally doing, we are giving preference to type 3, right? We are giving preference to type 3 on whom? Type 2 and type 1, right? We are giving preference to type 3 to type 2 and type 1. So that's why we are sorted according to type 3, right? So instead of sorting, and instead of using in one go, if I if I create edges according to type 3, according to all the type 3 edges in at first point, what I mean, see, if you see in this example 1, this blue line is for type 3. So if I give all the preference to type 3 and connect 1 2 2 3, after checking, of course these things are also checked. So 1 and 2 2 3 already already edges connected by this 1 and 2 and 2 3 for type 3 only, and then I will check only for 1 and 2 uh, according to the same concept. Then do we need to sort it? No, I don't need to sort it. If I remove this sorting and I will just use another for loop for this. So this is a for loop for only type 3, and I will use what I will use. I will just use another for loop for checking checking type 2 and type 1 only, for type 2 and type 1 only. So we don't need to really short this. We don't need to really short this. Why I'm doing here, see what I'm doing in the first loop. All the edges which have type 3, I am connecting all of them using that edges only, right? After that again a for loop, and I will check that whether we need an extra edges for Bob or for Alice. And if we need, after these edges, i will just I will just uh, if I need, then I will just join them and count it, right? And then I will just check it whether we are able to make components for all the nodes for Alice and Bob both, and I will return answer. See, so if I do this and using this for loop, two for loops instead of using one for loop, I will move this from e log e. I can change this time complexity to I can change this time complexity to O of e only, right? Because it will take only two traversal O of e plus O of e, which is again is only of O of e, right? So we have changes from e log e to O of e plus O of n, right? So that's the optimization we can done only using this two for loop instead of this shorting, right? So ultimately this question is for DSU. I will make a separate DSU to understand all these things, but I will attach a one article on CPP reference, CP algorithms uh, in a description. You can learn this because it's a very good article. You can simply learn one by one step and know all these concepts by one. But for now, if you don't know, just use this DSU template for that. Also, you use this DSU template more often if at any question you want to solve DSU problem. This is the same template you will use everywhere, just to save this and remember this DSU template and use this in any of the problem, right? Okay, and one thing is iota. This iota is on this is the same thing. If anyone don't know, it's the same thing like to iterate in this array n plus 1, and this is just a it is just a using uh, shortcuts for storing this value. So what it will do, it will start from 0 and store the value in increasing by 1, 0, 1, 2, 3, 4, like that, right? So it is same, this is same as like this is same like this, right? This is same as like this, that it start from 0 and assign 0, 1, 2, 3, 4, 5, 6 till parent size, right? This is the same as like this, that's why this is iota is given, right? So that's the whole question. I will just submit it and see that whether we have successfully because I need to put this in lead. Okay, something. Okay, this int type would be here and this is would be 0. Now I think this would work. Let's just run this. Yeah, let's submit it. Yeah, we've done. So that's the time and the space complexity for this problem. Hope you liked it. Thank you so much. Thank you so much. Bye bye.